Hello, AP Chemistry, and welcome to section 5.4. In this one, I think we'll cover 5.4 and 5.5. So the concept of heat of reaction and calorimetry, right? So a lot of this should be a review. So anyway, heat of reaction. So again, 5.1 through 5.3 was all about setting up the concept of enthalpy. What is enthalpy? As long as we're at constant pressure, enthalpy is heat, right? So the amount of thermal energy that is exchanged, right? And so now we're going to take the concept of enthalpy and heat and make it be of something, right? So this is our enthalpy, right? So delta H in and of itself just means enthalpy. Again, heat, right? The amount of thermal energy exchanged, right? Reaction, right? When we say of reaction, and when we say of anything, right? Because there's like a heat of reaction, heat of fusion, heat of vaporization, heat of neutralization, right? Heat of solution. There are all these heat of blank, right? And anytime we say heat of a blank, right, it means that it is tied to the stoichiometry of whatever process it's talking about, right? So for example, if we were talking about this process here, right, which is the combustion of methane, so we have CH4 gas plus O2 gas produces CO2 gas, and in this case, H2O liquid, right? Specifically 2 of these and 2 of those, right? So what that says is that this reaction is negative 890 kilojoules, right, for that reaction as written, which means we could say this is per 1 mole of CH4. We could also say negative 890 kilojoules per 2 moles of O2. We could all say negative 890 kilojoules per 1 mole of CO2, negative 890 kilojoules per 2 moles of H2O liquid. Yes? And likewise, right, if we were to say reverse the reaction, right, we would flip the sign on our enthalpy, right? That should make sense. Note that in your book, right, it does say that enthalpy is extensive, right? In that if we combust 10 moles of oxygen, right, we would release more energy, right? That makes sense. But here is where we need to be mindful that the enthalpy, or the literal amount of thermal energy exchanged, is obviously tied to quantity, right? But when we say enthalpy of reaction, right, that negative 890 is constant, right? So it's always 890 kilojoules released per 2 moles of oxygen. Yes? Does that make sense? Okay. All right. So then one of your practice questions gives you a reaction, and it says to calculate the quantity of heat released when 5 grams of hydrogen peroxide decomposes at constant P, right? So what would we do here? Right. We would take our 5 grams of H2O2, and then we would convert our 5 grams of H2O2 using its molar mass to get to moles. And then, we know that that is the amount, so negative 196 kilojoules per reaction as written per 2 moles of H2O2. Next up, calorimetry, right? So obviously, if we take a look at that word and think about everything we did last year, right, this is a way to measure, right, calories, right, to measure the amount of energy exchanged. And again, yeah, we should know this from last year, right? This is where we talked about Q equals MC delta T. Note that calorimetry is our experimental way of determining enthalpy, whereas everything else we'll talk about is more of a conceptual way to come up with enthalpy, a way to calculate it as opposed to experimentally determine it, right? Which means that we need to know masses, right? So in order to use this, right, we need to know masses, we need to know C values, and we need to know a change in temperature, right, in order to use this equation. And key thing, one of the things we tried to address last year, right, is that there must be a change in temperature, right? So if you were designing a calorimetry experiment because you wanted to measure like the heat exchange, right, or you wanted to come up with a C, right, because we could also use this equation and the heat exchange to come up with the C value of something, right, there must be a temperature change, right, meaning that one thing must be a different temperature than another thing, or whatever process we're studying must either release or absorb heat in order for calorimetry to work as a technique, right? So make sure you tuck that away and bear that in mind when you're answering questions. All right, so large beds of rocks are used, this is practice 5.5, in some solar heated homes to store heat, and here is the specific heat of our rocks, and we would like to know the amount of heat absorbed by 50 kilograms of rocks if the temperature increases by that. So Going back to sophomore year, right, don't forget, right, that the size of 1 degree Kelvin is equal to the size of 1 degree Celsius, yes, which is not equal to the size of 1 degree Fahrenheit, right? So what that means is, right, when we're talking about a change, because this is a delta T, right, and this is for a change, right, this is a change of temperature equal to 1 degree, or in this case 1 Kelvin, right? So, right, what that means is if it's in a delta already, right, there's no need to change it. We don't need to worry about the units, right? A change in Celsius is equal to a change in Kelvin, right? So anyway, we would just take this and plug this in, right? So we know that our Q is going to be equal to our 50 kilograms, so this many grams, times our C, which is 0.82 joules per grams Kelvin, times delta T, which is 12 Kelvin, right? And that would give us the amount of heat exchanged, right? If we want to know the temperature change that the rocks undergo, right, we would do similar math, right? We would be solving for our delta T if they emit this much heat, right? And so again, this goes back to what we talked about last year, where you should think about what is most comfortable for you, right? If you want to isolate delta T and then solve for it, or just plug everything in, right? It just kind of depends on whether or not you are prone to making silly mistakes or not, right? And we still have, that same number of rocks, or amount of rocks, I guess. And we still have the same C value. And we would just like to know what our delta T is going to be, yes? And we would solve for delta T in that case. All right, good here? All right, let's go do some calorimetry problems. So it says that, so first, this is our calorimeter, right? We've got our 2 nested styrofoam cups, right? Styrofoam because, right, excellent insulator, right? Meaning that all temperature exchange, as much as possible, stays limited to the inside of the cup, right? And so note that what that means is when we say surroundings, right, we're actually not talking about the stuff out here, right? So we need to be conscientious about that, right? And that's also true because we have this lid on it, right? That's key and important, right? And we have our reaction mixture in our solution, right? We have a stirrer, right? Obviously, we want to, if there's a heat exchange, right, we need to make sure that that gets distributed throughout the entire mass, right? Because when we use that equation, Q equals mc delta T, the assumption is that that entire mass undergoes that temperature change. So we need to make sure that whatever heat is exchanged throughout the entire mass, thus the stirrer, and then obviously you can't do calorimetry without a thermometer, right? So here, let's talk about what's happening, right? So it says that we have 50 mils of a solution is mixed with 50 mils of a different solution in a constant pressure calorimeter, and the temperature of the mixture increases, right? And the temperature increase is caused by the following reaction. So we have a reaction happening, and we'd like to know the heat of this reaction, right? So note that that's not just a Q, right? It's a Q that we then tie to the reaction. Yes, does that make sense, right? Assuming that the combined solution has a mass of this and a specific heat of that. So as we're thinking about this, first let's make sure we understand what our system and surroundings are, right? So here we have an aqueous reaction, right? So in here we have our AgNO3 aqueous, and we also have our HCl aqueous, right? And we're going to mix them together. So what that means is my system is this reaction, right? That's what I actually want to talk about. That's what I'm talking about in terms of the amount of energy released or absorbed, okay? Now, what I also need to think about is that what's my surroundings, right? What is the energy being exchanged with? And in this case, it's the water, right? Or we could say the solution, right? Depending on how we want to word that, right? In that the system are the actual components, right? The actual chemical species that are undergoing the chemical reaction, and the surroundings are everything else around it, right? So if we're going to solve this problem, first, we're going to start from the perspective that we can measure. So as this thermometer sits inside this cup, what that thermometer is measuring, right, is this bulk water or the solution, right? It can't literally measure an ion of silver as it undergoes a chemical reaction, right? No. But it can measure the temperature of the bulk solution, right? Which we can then translate into what's happening at the microscopic level between those ions, right? So let's read the question again, right? So it says the temperature of the mixture increases here, right? So that's our temperature increase. So that's the amount of energy being absorbed by the surroundings. And in this case, again, that is the solution. So I would strongly suggest that everything needs to be clearly labeled. I say that all the time, but I'm going to emphasize it one more time. So I would say that Q solution, or you could say Q water, it's fine. Q solution is probably better, is equal to, we're going to take the mass of our solution, so 100 grams of solution, times the specific heat of my solution, so 4.18 joules per grams degrees Celsius, right? And the temperature change undergoing for my solution, so 22.3. And that, right, so we've got mass of our solution, specific heat of our solution, temperature change of my solution, and that means Q solution is equal to, in this case, 338.58 joules, right? And so again, this is the amount of heat that was absorbed by the solution, which means that Q reaction is equal to negative 338.58 joules. Yes, as in the reaction, the actual interaction between the silver ions, the chloride ions, etc., releases 338 joules of energy to the solution. Yes? Now I can take that and tie it to what the question's asking for. It specifically asks me to tie it to AgNO3, right? So then my delta H reaction would be, first we would turn that into kilojoules, right? So you should, do your conversion so you're less likely to get it wrong. But then we have this, kilojoules, and we're going to divide it by our number of moles of AgNO3 that react, right? The number of moles of AgNO3 that react. And in this case, if we take a look, 1-to-1 mole ratio, same number of moles of each, right? So there's no limiting reactant. If we weren't sure of that, we would need to calculate a limiting reactant first and figure out how much AgNO3 actually reacts, right? Because it needs to be divided by a number of moles that actually participates in the reaction. So in this case, 0.1 times 0.05 is 0.005 moles of AgNO3. And then we would do that math to come up with our final answer. Yes? Because you're not going to give me a fraction. Yes, does that make sense? And that would give me the heat of the reaction from the perspective of AgNO3. Yes? All right. Next up. So here we have a different type of calorimetry, right? So we're not going to use one of these in the lab. Odds are if you take Gen Chem later, or if you go on to I don't know, do something cool like major in chemistry, right? Yes, you'll use bomb calorimeters at some point. But basically it's the same concept, right? Where we have heat that is released or absorbed, right? And then exchanged with a surroundings. And we know enough information about the surroundings to tie it back to the process happening, right? Units are a little bit different, but the beauty of this and most chemistry is that as long as we pay attention to the units, figuring out what to do is not that bad, right? So here it says that we have some lactic acid. Oh, so let's look at our calorimeter first, right? So again, we've got the stirring, right? To help make sure that the heat is exchanged with the entire amount of mass that we believe is present, right? A thermometer, because you cannot have calorimetry without a thermometer. Here in this case, we've got some ignition wires because our sample, right, down here is basically going to undergo a combustion reaction, right? If you do some reading, like this is how, you can determine caloric content of stuff, right? In that we would combust it, right, and see how much heat is released. And it's released to the water, right? And this whole thing is considered the calorimeter, right? The water and the metal part, right? So anyway, it says we have this many grams of lactic acid are in our sample cup, right? And burned because we also have oxygen present, right? And the heat capacity of my calorimeter is this, meaning that what happens is that every bomb calorimeter has its own heat capacity, right? So, and if we break that down, right, that's the amount of energy per change in 1 degree Celsius, right? That's the amount of energy that it will absorb for a 1 degree temperature change, right? And it says the temperature increases from here to there, right? So the heat of combustion of lactic acid per gram and per mole, right? So what that means is first we're going to figure out how much heat was released, right? So we'll take our 4.812 kilojoules per degree Celsius, right? And we will multiply that by our temperature change, which is 1.85 degrees Celsius, right? And that's going to give us 8.9 kilojoules of heat were absorbed by the calorimeter, yes? So this would like be Qcal, right? The amount of heat absorbed by the calorimeter, which means that the heat released by the reaction would be negative 8.9 kilojoules, yes? All right. And then we want to do lactic acid per gram, so it would be negative 8.9 kilojoules divided by our grams, which would be 0.5865 grams, right? And it also asks for, and obviously you would do the math, right? And then it asks for it for moles, right? So then we would just take our lactic acid, figure out how many moles it is, and then do that last step. Yes? Make sense? All right. That is calorimetry. Like I said, in the next parts of chapter 5, we talk about how to calculate enthalpy of a reaction using some different methods. All right. Thank you for listening. Be good, and I will see you soon. Bye.